Okay, so first things first, project one due Friday midnight, so I'll leave some time after class too, so like I won't rush out of here because I know some of you have questions. Kenneth and I were talking. There was a typo when I copied and pasted this over. I copied and pasted the numbers from above, but that did not change the actual and I changed the month, so it looked very weird. So this is now updated to where this is test case 2 is correct. So I changed the salary from what was 120,000 to 80,000. The decimal was 0.15 instead of 0.10. The cost of the home was 500,000, not 100,000. And then the decimal for the payment and the annual rate of return were the same. But again, remember that while I provided 2 test cases, you should make sure your program is robust enough that it works with other ones, because I've basically hidden some test cases from you to see if you've really thought through and understood the logic. I provided all the test cases up above, so make sure you kind of think through that, and I would make that recommendation right here. Consider different possible inputs and how they should be handled. But I did say I am not going to be worrying about like your user being mischievous in the second part. Like they're not going to throw in like, what would you like your rate of return to be? ASDF. I'm like, I can't do much with that. So you don't need to guard against those things. But that project is going on. The other thing that we're working on is there's some exercises due tonight. So if you have questions, feel free to hang out after class. Or if that doesn't work for you, let me know and we'll arrange a time. Does anyone have any questions with anything related to the goings on of the course? Cool. Okay, so what we're going to do today is we're going to talk a little bit more about bisection search, and then we're also going to just introduce the basic idea of functions, where you could write your own. Hey, Alejandro, can you grab the lights for me, just to make it a little bit easier on all of our eyes? Okay. So if you remember last class, we worked with exhaustive enumeration. So this was the code we wrote at the end of last class, where we are asking the user for some input. And again, we didn't even have to say it's an integer. We just said, give us some input. And we tested if that was a perfect square. So the way we did that is we basically started at 0. We squared that, and we repeated until we exceeded x. And again, what we'd found, if you went ahead and put some input that was a perfect square, so like 144, it would go ahead and tell you the square root of 144 is 12. And notice that it took the number of guesses that was 12 here, because again, we had to check 0, we had to check 1, we had to check 2, we had to check 3, we had to check 4, all the way up to 12. So this is great until you get an absurdly large number like that one right there. Still reasonable, but we can go ahead and eventually, I repeated 1 through the top row of the keyboard 3 times. You can see the program's really going to slow down. To the point like, really? Are the computers this slow? I mean, imagine if you're taking a test and your calculator's taking that long to compute the number for you. Like that would be terrible. And this rambling is still not done, but it's still iterating through guessing. So we introduced another type of, or I briefly mentioned it last class, we're going to learn how to do it by paper, and also to go ahead and program it here in a moment. Does anyone remember the type of search that I introduced at the end of last class, what it was called? Yeah, it was a bisection search. So let's go through the basic idea of a bisection search. So you may want to just kind of grab a piece of paper or something if you want to take notes on this, but of course I will go ahead and post it later. So let's aim that at the board, so that'll work. Okay, so the way the bisection search works is as follows. What we're going to do is, let's say we wanted the square root of 16. Start with something very reasonable. The way you would do this, let me give this if you want to take some notes. If you want. The way you would do this is you would start with some reasonably small number. And let's go ahead and, of course, We know square roots are positive, so we're not going to worry about complexing. So we're going to have our smallest value here to be 0. And then what we're going to do is we're going to consider the highest value to be the input of the user. So the user wants to know the square root of 16. So before, what we would do is we would check 1, 2, 3, 4, 5, 6, 7, 8, 9, colon, and we would keep squaring, but we would eventually find that the answer is 4. So it would take 3 iterations. So not too bad, but the numbers are small. So the way bisection search works is you start with a low value, and then you have a high value. And then what you're going to do is you're going to bisect it. Bisect means right in the middle. So you're going to consider 8 as your first guess. So what you're going to do with that guess, you're going to square it. So if you look at 8 squared, that is going to be 64, which is greater than the 16. So because that is too high, what we now know, that is all worthless. We do not need to check anything over there. We just cut our problem in half, which doesn't sound like a big deal, but if you're dealing with like, I don't know, a couple billion, it's nice to all of a sudden in one fell swoop get rid of half of the options. So what you'll then do is you're going to update your guess to be the new high. So what you'll now have is 8 is your new high, 0 is your new low, and you're going to take a guess which bisects it, which is going to be 4. So this is my new guess. So now you go ahead and check 4 squared. That is equal to 16. So you're going to go ahead and basically return, hey, the square root of 16 is 4. So if you think about it, it took half the number of steps to go ahead and get the answer. Our exhaustive just checking one number at a time took us 4 steps. This one only took us 2 steps. So much more efficient in terms of the actual solving. And of course, if this was too low, then you would go ahead and update your low value. So I think there was a slide on, yeah, so this right here is essentially this is the same scenario, so still with the square root. But that is the idea of a bisection search. It works very well, like if you were sorting well, hold on, I should say this way. If you were looking for something and that was already sorted, the condition that this works well is that you start with something as sorted. So we're going to learn about arrays here in a few weeks, maybe not even a few weeks, maybe next week. And we'll go ahead and it'll just be a container that if it's sorted, we can easily search for a certain element in it. All right, so that's bisection search. Let's go ahead and code it up. And so we don't have a video of me. Let me go ahead and switch this back to there. Okay, so again, if you want to go ahead and save this, it was in last classes, so this was just guess and check.py. I'll save that in case we want it for later. But let's go ahead and actually code up bisection search. So what we're going to need to do first is ask the user for input. Let's go ahead and cast it to an int. Let's go ahead and put some basic prompt in there so we're not just staring like what are we supposed to do next? Oh yeah, it wants us to type something. We're going to deal with that one before actually did not find the square root. It just checked if a certain number was a perfect square. So what we're going to go ahead and do is maybe a little bit more impressive or more desirable, but we're going to actually find the square root. Square roots can be floats. So remember from last time, we do want to go ahead and put some bound on our error when it comes to working with floats. So we'll define epsilon. For a bisection search, you're going to need some low value. For our problem, it does make sense to go ahead and just set low to be equal to 0. So again, find the square root of a number x. It might be a fun little exercise. I don't know if I'll make it a programming exercise or not. Haven't decided. I'm going to work on that tomorrow night. But it might be interesting to see if you could generalize this to handle cube roots, because then you have to consider negatives as well. Oh, that would be a tough one, so it may be worth a little more. But so we have our low. We also need our high value. The high value will be the maximum of 1 and the input. The reason we put 1 there is because if we have, it's basically to handle a corner case where if we were asked to take the square root of something that was like 0.5, we want to go ahead and maybe start with a nice integer value. So that's that case right there. That might also be worthwhile if you consider like negatives and things like that. So the guess that we're going to take is going to be the midpoint, the bisection. So we're going to take high plus low and divide it by 2. That will give us, if we were using 16, that'll get us our 8. And just to understand the power of this, the number of guesses, I'm going to go ahead and say, okay, that was our first guess, so I'm going to start that out at 1. And while we're going to enter a while loop. While the guess squared minus the value we're looking for, its square root, is greater than some or equal to some epsilon, we're going to go ahead and keep searching. So greater than or equal to some epsilon, we're going to keep, this is our basically, we're going to search. So one other thing to note, this is just a personal preference, but just to make sure that we don't accidentally end up with some sort of negative, is common when you're testing the difference between two things as compared by some, if you're just checking for error, you do want to consider the absolute value. Because remember, floating point is pretty close. So it might be that the bits are just above. So if they are, then it would be negative. So you do, whenever you're checking for the distance between two things, make sure that you think about mathematically distance is the absolute value of some difference. So that's pretty common. That should actually, you should immediately be thinking this idea back to the formal definition of a limit from Calculus 1. Okay, so for our search, what we're going to do, let's just kind of keep track of things. So you don't have to do this, but it's nice just to see what's happening. So let's go ahead and keep track of our low. Call that low. Let's track of our high. We'll call that high. Let's go ahead and keep track of our guess, and we're going to just print some information as we iterate through. All right. So if the guess squared is less than x, this is the case we ran into here. So our guess squared is, well, this is not the case we ran into here. So this is the case that if we're on this side and we'd want to limit here. So again, you can handle either of these cases. So I think this is the way the textbook did it, so I'll match it that. But in general, a bisection search, if you were to go ahead and square, is too low. That means you need to go ahead and check the high side. So what you would need to do is update your low to be the guess. So if your guess squared was too low, which mathematically it wouldn't be because we're talking about square roots and square roots bring it down. But in general, a bisection search, if your guess was too low, then you want to go ahead and get rid of the left side and only work with the right side. And you work with the right side by updating your low to be whatever your guess was. This is the else scenario is what we ran into. That is to say the guess squared was too high. So this is the scenario that our high is now our guess. So that chops off the right side of the problem. But this is kind of the common mistake. Don't forget to update your guess. So Kenneth and I were talking about this before. I think there's a temptation as we're thinking like, oh, okay, we updated our high and our low, so our guess must have been updated as well. Well, the program doesn't step back and say, oh yeah, I'll update this for you. You have to explicitly say, actually, the guess needs to again be recomputed to be the midpoint. So So remember that the computer is the greatest listener you will ever meet. So don't say bad words at it because it knows. I don't know. Probably not. Okay. So this is it. This is the algorithm right here. So let's go ahead and just exit the while loop. So notice here we are outside the while loop. And we're going to go ahead and print the number of guesses. And so let's just see how many guesses we took. Number of guesses. Although to make this worthwhile, we should go ahead and actually, you know what, if we got through all of this, we do need to increment our number of guesses by 1. So num guesses plus equal to 1. So if we actually want to know how long this algorithm took, we need to update that. And our answer is going to be, we'll just write it as an F string. We'll just say the guess is close to the square root of x. Well, and we'll just call that x our input. And I want to say close to because, well, we'll look at an example here in a sec. Wow, look at that. That program is still not computed, is still not checked if that is a perfect square. So that was a terribly inefficient algorithm, don't you think? So I'll remember this number. Let me copy it, and we'll see if the bisection search was actually able to do this in a reasonable amount of time. So I'll copy that for later, so I'm going to stop that. It had its chance, too slow. So let's go ahead and run this and see if it does what we expect. So I'm going to run, I'm going to type 16. And you can see that's what we expected. It took the one guess at the beginning, so it was low as 16. The guess was 0.8. And then it went ahead and took the next time through, it went ahead and it updated that. So that's where num guesses increases to 2. But then it found that 4 squared was equal to 16. If you were to type something a little bit larger, let's go ahead and do that number. And let's see if it's able to go ahead and find the square root of that thing. It's taking it a moment. Let's see if, oh, by the way, while this goes, this may be a good opportunity for me to mention, printing something to the console is slow. So like if you're like doing some fairly large computation and you're using print statements to debug, this really slows down how fast you're going to get to the answer because this is a pretty slow operation from the computer standpoint. So let's go ahead and stop that. Let's interrupt that. I'm going to go ahead and comment this out. Didn't mean to. So I'm going to comment this out and now run it. Give that same output. And it's still a fairly large problem, but let's see within a reasonable amount of time if it'll get it. I don't know. I didn't check this number. But while we're waiting a moment, does anyone have any questions? Yeah. You're getting an error. So let me take a look. Misspelling. So frustrating, right? All right. So honestly, still this number is a little bit out of reach of this algorithm. There's other algorithms that we'll learn about later in the semester that might even be better, such as I think we'll hopefully get down to like, I can't remember what the ones. We'll do a lot more sorting than we will searching, but let's go ahead and make this a little bit more reasonable. So alas, that algorithm's even still too slow, but your calculator probably could do that number. I wonder if Google could. I wonder the square root of that. Would Google could do it. Look how fast Google did it. And that doesn't even go to account the actual network transmission. So there are better algorithms than even the ones for coding because, well, if Google did it, why can't we, right? Okay, they're pretty smart. But you can see this algorithm, even for a fairly large number, let's do something like that, is going to, well, wait a minute. Wait a minute here. Let's look at this. Let's try this. Okay, yeah. So it is. You could also maybe increase your epsilon. Or change your epsilon, that would maybe speed it up. So it still is not the fastest, but compared to the one from earlier, a lot fewer steps to go ahead and compute the square root. So that's bisection search. Yeah, Anna, question.
So I put in 25, square root of 25 is for sure 5.
Mm-hmm.
And it put in it has 20 decimals, x of 5. That's the answer.
But it still got it, right? The answer is still within, so it's still got the square root of 5. So one thing you could go ahead and do if you really want your answer, see it like this, that's kind of annoying square root. There is a function. Let me go ahead and just do it. It's called round. You could round your guess to 2 decimal places. So if for some reason you want to go ahead and just clean up the answer, the rounding is a function to go ahead and clean that up. That's maybe what's helpful. Okay, any other questions? So here's a fun little question just to make sure you understand bisection search. Let's suppose, has anyone ever been in New York? Anyone been in New York? Empire State Building? I haven't. My wife went without me. Thanks, Becky. So there's this fun little scenario. Let's go ahead and consider this. Down here at the bottom, I don't want to give the solution, but I want to give you a moment to think about this. Come on, there we go. The Empire State Building is 102 stories high. A man wants to know the highest floor from which he can drop an egg without the egg breaking. So a little typo there, without the egg breaking. He proposed to drop an egg from the top floor, and if it broke, he would go down 1 floor and try again. Again, thinking about that, top floor. At the worst case scenario, how many eggs is he going to use? 102. That is to say, every drop, the egg will break. So that's a lot of eggs. But at worst, again, it says this method will take 102 eggs. So in the worst case scenario, again, the egg always breaks. How many eggs would be used if you were to use a bisection search? So think about this a sec. Go ahead and maybe run through the bisection search algorithm just on a piece of paper. Try a few things. It's less than 51. 51 was too high. Let me give you maybe about 2 minutes to think about it. Ask your neighbor what they're thinking. If you have a question, ask your neighbor. I'm going to take a sip of water. You know that. Why is that number, Anna? Kenneth might be able to explain it too. I'll give it a sec. Go and ask your neighbor, or you can all stare at the computer and I can just chill. That's fine too. By the way, questions like this are also great sort of test questions. All the questions on the test are not going to be, do you know how a certain syntax works? It's going to be, do you understand kind of the algorithm or the fundamental that's happening underneath? All right, so maybe about another 17 seconds. All right, Anna, what do you think?
Me?
Yeah.
So my logic was, it's always gonna break whatever floor you have.
Okay.
So I just bisected each time, and each time I bisected, I counted.
Okay.
So until I got to 1.
So it would be more than 1.
Well, it's still 7 eggs until I got
7. Oh, okay. Until your actual computation, and that is correct. 7. So basically, if you're looking at this, here's the solution. How I'm considering my guess each time. So it didn't work on floor 102. I checked floor 51. Then I checked floor 25. Then I checked floor 12, all the way down until I checked the ground floor, which is 0. So it might be interesting to also start thinking about this. And I've mentioned this pretty much anytime we talk about algorithms, In the worst case scenario, it took 7 attempts. If you notice that 102 is, if you consider log base 2 of 102 is approximately 7, which is indeed the answer. So this is worst case scenario. You're like, oh my goodness, that is terrible. And that's sometimes why they call that big O notation, because like, oh no, okay, more on that in a few weeks. But start to make those connections. So any questions on bisection search? All right, so spend some time with it. I think I'll try and find an exercise for you guys to try in your homework or in the exercises. The other thing I want to go ahead and do today is introduce the basic idea of functions. So we've been using functions up to this point, and honestly, this is not very reusable code. If you think about this, every single time you want to go ahead and find the square root, you need to go ahead and ask the user for input. It would be nice if I could go ahead and have some sort of construct to go ahead and be able to test in many numbers as I need to back to back. And that's kind of what automated testing is doing, but we want to go ahead and get that stuff. So I'm going to go ahead and delete this. Again, I'll post the notes later. So what I want to go ahead and do is show you how to define your own functions. So let's go ahead and let me show you how to do that. It's pretty easy. So you start by typing DEF. Yes, you heard me right. You're not deaf. DEF. That was a terrible joke. DEF for DEF for define. Then after that, you'll go ahead and name your function. I'm going to name it my function. I'm going to put 2 parentheses, meaning this function does not need to have any input. I'm going to just say this function is going to do something. Then you put a colon, new line, and by the way, notice that I am indented by 4 spaces. So this is now the block right here. So this only thing this function is going to do is print my first function. Very cool, right? Like, what's your first function do? It prints my first function. It's like My Little Pony, but no, it's my first function. Okay. So let's go ahead and run this. And if you run this, you'll find absolutely nothing. So we have to think about why is that? Because all we've done is defined the function, we haven't used it. This is like, oh, this is what the function is at the top. So in order to use that, you're going to go ahead and just on line 5, I'm going to just go ahead and type the name of the function with the parentheses. And now if you run it, you can see it says my first function. So this is nice because let's say if you're really excited about this, you can be like for I in range of 10, then you can go ahead and just call that 10 times and you can be like my first function. Very exciting, I know. But we now have a way to kind of repeat things, and even more than one line at a time, we can now have a way to define our own function, and it cleans up code. Maybe a quick word, by the way. Before these 6 lines of code, everything we had learned about is all we need to basically write any program. That's something a property knows, Turing completeness. So everything from here on out is really just niceties. So any program you want could have been written with the concepts we've already learned about. Let's take a step back, and I want to go ahead and just mention something about, okay, so you may, you have my function. If you put the parentheses here, it will go ahead and print it. Other things, if you noticed, like you can print my function. Let's see what this does though. So I'm going to print my function. So the first thing it does is it prints my function. This second my function is being printed when the print function or my function is being called in here. By the way, when we use a function, another time it might be referred to as called. We've called it. But note this none right here is showing up because this print is printing whatever the result of this function is. And again, we're going to go ahead and talk about the return value of functions next. So I'm going to go ahead and just kind of illustrate it right here. If I go ahead and type the word return, when the function is done executing, it is going to go ahead and return some value to whatever called it. So what called it is this other part of the program. So let's go ahead and say it's going to print, or it's going to return the string that was fun. So now if we run this, you see a couple things. The first line right here of my first function comes from line 6. The second print my first function comes from when it was called here, and then the that was fun is the printing of the result the function returned. And again, if you want to, you can always go through a debugger. It might be interesting to see how it goes through the debugger. You can see right here on line 6, it's going to go ahead. Next step, it's went inside the function, so it jumped back up to 3. The next line is going to go ahead and print my first function. It's going to now return that, but it didn't do anything with it because it didn't need to print anything here at line 6. But then it's going to go down to line 7. It will end up back in that my function, print the my first function, because that's what the function does, and then it's going to return the result, which will then be printed by the print function. So a lot of little things happening there, and just like 5 lines of code, again 7, but a couple blank ones. So that is how you do a function. Any questions there? So a quick little exercise. So just to see if you exercise. Go ahead and define or write a function that returns the absolute value of an input. So before I get free you, I do need to go ahead and say, okay, we're going to define our own absolute value function. So I'm going to go ahead and just call it absolute value. And then instead of an empty parentheses, I'm going to put an X in here. So write a function that returns the absolute value of an input. So I'm going to give you a couple seconds to think about this, and then we'll kind of talk through it. So what would you need to put in here? All right. So again, you might have had some success on this, but let me go ahead and kind of talk us through it, and then be able and go ahead and explain some of the terminology associated with it. Okay, so first thing I should say, so this X in here is known as a formal parameter. So this right here is known as a formal, so X is a formal parameter. It is the input to a function. So what's going to happen, just to kind of illustrate this, whenever you call a function, let's go ahead and just call the absolute value function that I'm defining down here with a number 5. And if we run this, notice that it printed 5. So what happens is when a function is called with inputs, the number that was passed in to that function, again, this 5 right here, I'll say right here, 5 is called the argument. Whenever an argument is passed into a function that you have defined, it is binded or assigned to this variable x, and then you can go ahead and work with that value that was passed in when it's assigned to that variable that was defined in the first line of the function. So you can see right here, if I were to go ahead and change this to 10, whatever argument is passed in is assigned to the formal parameter. You could even have more than one, so you could like print x comma y, and you can go ahead and say like 10, 7, and you can see you can now work with like, I want to print y plus 1. If you run this, let me zoom back out, you can see that it is 10 and 8. So you can have technically infinitely many formal parameters, but the absolute value, we only need 1. So the way we're going to do this is we're going to, let's go ahead and clean that up. Just make that a 5 again. So instead of printing, I don't really want this function to print something. I just want it to tell me what the absolute value is, and I don't even want it to tell me. I just want it to compute it. Don't say anything, just compute the absolute value. So the way we would do this is we would say if x is less than 0, what we're going to return is the opposite of x. This is basically the piecewise definition of the absolute value function. Otherwise, or else, just return x. So this right here is the, let's see if this makes sense. In the case of number 10, if we run this, it didn't print anything. Why didn't it print anything? I didn't tell it to. It just returned it. So what I need to go ahead and do is add, hey, print the value that is returned from the absolute value function that we defined. So it is 5. And just to make sure, let's go ahead and also just copy and paste this and try a negative number. Let's try -5, and let's go ahead and also try 0. I'm trying a bunch of different things, and if we print this, 550. So this is actually really nice because we have one function, we can reuse it. The other thing that I want to go ahead and say about functions is it's good practice, especially if we have a lot of different functions in our program, to describe what they do. So what we can do is good practice, and we'll start talking about style for exercise or for project 2, is I'm going to use a triple quoted string. So we saw this in an exercise. This is a valid string, triple quotes. So what we'll go ahead and do is just describe what it does in here. Returns the absolute value of the input right here. So this line right here is known as a doc string. So if you guys have turned on IntelliSense, and let me just go and turn it on. It is enabled here, I guess. And if I were to type print, parentheses, do you see all this information? This information is being generated by the doc string. So if I were to, I wonder if this will work. Absolute value, I don't know. If I were to do here. So notice when I put parentheses, it is once I've put in this doc string, it will go ahead and if you have a code editor that is using code intelligence, it is reading the doc string and basically returning information to the user about what this function does. So this is, if you were to ever, as you write more code, make sure you document this, what your methods and your functions do. At the end of the semester, you're going to do project 7, and just preview project 7 is basically build your own project. where we're at that point have introduced two modules known as either TK Enter or Pygame, which are visual graphical user interfaces, and you're going to have many functions in that, so make sure they're documented, and that will be part of the rubric. It's just good coding style, and we'll start getting into that more. But again, what did I say this line is called? Did anyone catch that? It is called a doc string. You've got it, Doc. Okay, so anyone have any questions? Let's do this. This is a good stopping point.